In this video, we are going to cover a question from rotational motion in which there is a rod which is at 30 degrees from the horizontal and is released from rest. We have to find the angular velocity of the rod when it is passing through the horizontal. So, see, I know rotational motion questions are scary to many students, but when you approach the question with the right thing, with the right equations, you will never fall in its trap. So, let me help you with with the approach. First, see, in this question, we need to find angular velocity. So, we need to understand what the question is asking, and based on that, the formulas that we, like the formula booklet that we have, alright, for the particular question. So, for angular velocity, the first thing that comes in our mind are these formulas. These are some simple equation of motions which gives our omega. Apart from them, there is this momentum conservation equations where you find I1 omega 1 equals I2 omega 2, right? And the other part is energy equation, or you can say work done equation, in which work done by torque equals change in kinetic energy, delta Ke. Alright, because in delta Ke we have this half I omega square minus omega initial square and the work done by torque, which will be nothing but tau d theta integration. Alright, so in all these things we have omega with us, and lastly we have the Newton's second law of motion for rotational equation, which is tau equals I alpha. Now, apart from them, I don't think so that we have anything else that we can solve the question with. Okay. So, before proceeding further, we should understand that momentum conservation equation and these three equations, they are applicable only if alpha is constant. Alright. And if it is not constant, then we are only left with energy equation. So, how can we see that alpha is constant or not? First of all, let's see whether there is alpha or not. Alright. Now, since this rod is starting from rest, so its omega naught is absolutely 0. Alright. Initial omega. Then at 30 degrees, there will be some omega because it is rotating. Right. So, omega final, we don't know. That is what we are yet to find in the question. Alright. So, that means alpha is there. But whether the alpha is constant, it is yet not found. So, to find that, we will use this equation. If alpha is constant, like how can you say alpha is constant? We can say with the help of tau, because I is the moment of inertia of the rod, which is certainly constant, which is not changing. You may find in some question that it might change, but here it is not changing. The shape is not changing at all. Alright. Then our torque. Let's see what our torque is. Now, since we have this rod, okay, and this is the point of hinge. So, first of all, think of it why this torque is rotating at all. It is rotating because of this mg that is acting here. Alright. Is there any other force that is acting on it? No. Alright. So, that means this mg is producing some torque, some motion in this direction, which is making it to have some alpha. Alright. Now, this mg is like this, and we know that this force will be having component in this direction as well as in this direction. Now we know that this component of mg will not cause any rotation. Why? Because this is passing through the hinge, and we know that torque's formula is R cross F, and for the cross product, the angle between the R will be acting in this direction, it will be in this direction, and if F is in this direction, then the angle will be 180. right? So the torque will be 0 because of that component. Then mg cos theta, which is this component, will be having the torque, and this distance is L by 2. So here we have the torque. Alright, now see, the torque is defined by this and it has theta in it. Now when the rod is making motion from 30 degree to 0 degree, what is happening? Theta is changing. Theta at some point will be 15 degree. So it is changing. Since theta is changing, that's why tau is changing. Okay? And since tau changes, alpha changes. Which brings to our conclusion that alpha is a changing quantity and we cannot use our equation of motion or our formula, equation of motion or the momentum conservation. So we are only left with the energy equation. Okay, so let's proceed with the solution now. So tau d theta integration will be equal to I omega square minus omega naught square. Alright, so why I am directly writing this and there is no half mv square component? It is so because it's a pure rotation question. There is no translation involved. That's why we are able to write I omega square. Alright, now the tau from our previous page was L by 2 into d theta. We have to integrate it and we have to find I. We know that omega naught is 0. That's why we are only left with omega square, which is our answer. Alright, now theta. Theta here is changing from, see, since motion is happening in this direction, that's why we have to take the angles from this line, right? This is our 0 line, then it is going towards down here, right? So it is starting from 0 to minus 30 according to the sign convention, according to plus 30, sorry. Alright, so this will be mg sine theta 0 to 30 and L by 2 is a constant and we have I. So I we need to find at this point. At this point, see, if we have a rod, then moment of inertia at this point is nothing but ml square by 12. Alright, now using parallel axis theorem, we need to find the moment of inertia at this point, which is nothing but m r square, and r is the distance between these 2 points, which is L by 2, which gives us ml square by 3, right? And we have omega square. Okay, so after doing the calculation, what we get is omega equals under root 30, which is our answer A. Okay, so you see this question wasn't very tricky, and after ruling out our equations that we could have applied, we are easily able to find the solution. Okay, so if you have any more doubt about this question, you can ask in the comment section below, and if you have any other questions that you want me to put in our other videos, do email us. Thank you so much. Have a nice day.